started today. First order of business is that someone pointed out correctly that I had set the coding portion of the final to be on Wednesday, November 30th, which is during the study day. And that doesn't work. Obviously, it worked for some of you. It won't work for others. However, there's a fairly easy solution, which is that I had originally planned to cancel class on Thursday, December 1st. And instead, we will be doing the coding version in class on Thursday, December 1st. So in here, you will need to bring your laptop with you, okay? Because it will be done on your laptop. So you will need to bring your laptop with you to class on Thursday, December 1st. You'll have the full hour, 15 minutes to do it. There will be 2 questions, and you'll have a 1-page cheat sheet, front and back. Let's see, what else? There's guaranteed to be 1 question on recursion. The other question is going to be involved with somehow linked data structures, either with linked lists or with binary search trees or trees in general. So 2 questions, hour, 15-minute. Bring your laptop. We have no guarantee that we will be able to use the Hydra Labs. Okay, I believe you don't have a laptop, which you're supposed to, but if you don't, I believe you can get one from the library or OIT or something. You can apparently check one out or something. You'll have to look into that. Okay, but there's no guarantee that we will be able to handle people in the Hydra Lab. So bring your laptop. Okay, and I would recommend that you have Firefox loaded on your laptop. That is the software that Code Assessor runs best with. So bring your laptop. It may well be that if you don't have a laptop, you're going to have to do it by hand. So that may well be the alternative, is that you will have to do it by hand if you don't have a laptop. Okay, and then, so that's the coding. The in-class portion of the final will be at the normal final time and will be like a midterm. You'll actually have an hour, 15 minutes in which to do it. And it will cover material since the last midterm. It won't be cumulative, although obviously cumulative in the sense that you're expected to know everything. Just like on the coding portion last time, you're expected to do a printf statement. Okay? So, any questions? Yes?
And the written portion will just be in this room?
Yes, the written portion will be in this room. Like I said, during the normal final time. Other questions? Okay. Okay, so we are continuing today with binary search trees, reviewing their operations and what they are, and then looking at some of the code that you can use to implement them. You'll remember that a tree has a root, which is the topmost node. Conventionally, we show trees top down. It's obviously possible to show them left to right or bottom to top, but we show them top to bottom. So the root topmost node has no parent. Okay? In a single node tree, the root could also be a leaf. So doesn't have to have children if it's a single node tree. So this is the root. The internal nodes, or interior nodes, I'll call them both, are the nodes that have both a parent and children. And the leaf nodes, whoops, this daisy is not a interior node. The leaf nodes are the nodes that have no children. Okay, and we talk about the height of a tree. Does anyone remember what the height of a tree is? Yes, Ryan.
Isn't it just the number of elements that are in the longest chain?
So yes, but be a little more specific. Sorry, I just need to get a little more.
The distance from the root to whatever node minus 1.
So it's the length of the longest path from the root to any leaf. Okay? So length of the longest path from the root to any leaf. And the depth of a node, we talk about the height of a tree, we talk about the depth of a node. Depth of a node is the length of the path from the node to the root. Okay, and actually one way to think of the height of a tree is the maximum of the depth of any node. Although not the way we typically do it, but that's the relationship between height and depth. Height's kind of a top-down concept. Depth is kind of a bottom-up concept. Okay, and last time we gave recursive definitions for both height and depth. So a binary tree is one in which no interior node has more than 2 children. So a binary tree, I'm not talking about a binary search tree yet, I'm just talking about a binary tree, is a tree in which no interior node, well actually no node, has more than 2 children. A binary search tree is one in which at each node, all children in the left subtree have keys less than or equal to that node, and all children in the right subtree have keys greater than or equal to that node. So a binary search tree, BST, equals a binary tree in which for each node the children in the left subtree have keys less than or equal to the node, and children in the right subtree have keys greater than the node. So what you see up there are all examples of binary search trees. Finally, trees are recursive. So a tree, a single element, a tree can be the base case for a tree, is a single node. Okay, it is both the root and a leaf. Then Also a base case is an empty tree. Okay, that's also allowed. So a one node tree is allowed and an empty node. And then the recursive case is where you have a node with a left and a right subtree. Okay, in fact, in some sense, this base case is superfluous because it is handled by this base case, right? Because this base case is the case where each of these two subtrees is empty. So I just did that first base case for convenience. Okay, so that's basic tree terminology. Now, the nice thing, okay, so these are examples of non-binary search trees. On the right is simply not a binary tree. On the left, some of the keys, such as Daisy, Luigi, Luther, and Waluiga, all are in the wrong place. Okay, Waluigi is at least in Binky's right subtree, but should be to the right of Fred Yen. I can't pronounce it, so. Okay, so we have three operations we want to perform on binary search trees: insert, delete, and find. And ideally, we will end up with a fairly balanced tree. Remember, if we end up with a fairly balanced tree, the height of the tree will be roughly log n. And therefore, because each search eliminates half of the tree, at each point you either go left or right, thus eliminating half the tree, you will come to a leaf node after log n comparisons if it's balanced. Okay, so that's why with a randomly generated or a random set of insertions, a binary search tree tends to have order log n, insert, find, and delete. Now, we showed you last time that a bad insertion order could defeat that. So here, where the items were in sorted order, you'll end up with a linear list. So it's possible to have bad insertion orders. We'll take care of that problem next week, and actually starting Thursday, so not even both Thursday and next week. Okay, so find and delete are pretty simple. So find is simply going to the root node, and if the key we're looking for is greater than the root, we go to the right. If the key is less than the root, we go to the left. So our search trees, well, let's see. Let's do some code. So we're going to use a Sentinel node for our binary search trees. And our search nodes are going to have a left and right child pointer. They're also going to have a pointer to the parent. They're going to have a key and something you haven't seen perhaps, a void star value. So void star, you've seen void as a return value for a function, but you've not seen it as a pointer. Void star is a generic pointer. So it can store any type of pointer, an int pointer, a string pointer, a float pointer, pointer to a customer. It can store any type of pointer. So we call it void star to indicate that it's generic. Now, C++ doesn't really make use of void stars because it makes use of a template mechanism that allows you to specialize a data structure to a particular type. But in this case, Dr. Plank is showing you an old school trick. This is a C trick that used to be used when templates didn't exist and is still used in C to allow you to point to a value of an arbitrary type. Okay? Now, you'll notice you can't actually store objects themselves as values. I can't store an int here. It must be a pointer to an int. I can't store a string. It must be a pointer to a string. So it's not as general as a template, because in a template I can store either the object itself or a pointer to an object. But he is doing his best to make it a generic structure without introducing the machinery of templates, which is fairly complicated. We don't get you to that syntax until the junior course in which is a programming languages survey course. So declaring something as a template class is actually fairly complicated. So this is what's happening with the void star. Okay, then his class, his container class, so just like with lists, what we have is a container class. So a BSTree is the container class, and it's going to have a sentinel that points to a node. And the root is actually going to be, of the tree, is going to be the right child of the sentinel. So the first value that goes in, like say Binky, is actually going to be the right child of the sentinel. Just arbitrarily defined as the right child. We could also have arbitrarily said it was the left child. We just make a choice. Okay, so you see here protected sentinel node. Also a size, and we'll get to this when we get to it, so don't worry about it for the time being. We have a constructor that sets up the tree, a destructor that destroys the tree, an insert, find and delete, something to print the tree, to pretty print the tree. Again, we'll show you that when we get to it. Something to return the size, something to indicate if it's empty. Now, if you're really doing this in C++, you should use a bool as the return value, but Dr. Plank is old school, so he uses an int. And then 3 so-called helper functions. Notice these 3 helper functions are protected. So it will turn out that the print uses a helper function called recursive in-order print. It will turn out that the routine to return a sorted vector, which is going to return a sorted array or sorted vector of values, not of values, that's going to return a vector of values, and it's going to be sorted by key. And finally, the destructor will need a recursive destroy helper function. So these are helper functions that are protected because we don't want them part of the public API. There's no reason for them to be made public so someone can see our implementation. So I'm going to start with the couple of the easy ones. So we will look first at, where do we go? Okay, here's actually a sample view of a binary tree. So this one actually is one in which we have the parent as Fred, the left child is Binky, and the right child as Luigi. So this is conceptually what it is. So you can see the size is equal to 3. We have a pointer to the sentinel node. We don't care what its key or value is because it's not really part of the tree. So its right pointer points to Fred. So here's the key with Fred. You can see that Fred's left pointer comes down here and points to Binky. And you can see that Fred's right pointer comes down here and points to Luigi. Now, one difference from the book I believe had no pointers for the children because it wasn't using a sentinel, but we're going to have the children, or the leaf nodes rather, point back to the sentinel. So you can see that for the children, the left and the right nodes all point back to the sentinel. So that's how we'll know when we've reached a leaf and have no farther to go, is if we try to follow the child link and we come back to the sentinel. So questions about this layout?
I have a quick question.
Yes.
So what's more useful, to have the sentinel where it goes back or to have like null pointers at the end?
So the question is it more useful to have a tree with nulls, or is it more useful to have a tree with sentinels? And the answer is, just like with lists, it's more helpful to have a tree where the leaves point to sentinels because it makes insertion easier and find and everything else, because you always know that you're going to encounter a node in the tree. You don't have to distinguish between a boundary case where something might be null and the other cases where it might be non-null. So basically the sentinel node is guaranteeing that it's eliminating your boundary cases, just like it eliminated boundary cases in the case of a linked list. In fact, I'll show you when I get to the insert algorithm. I'll actually show you the books insert algorithm, and I'll show you the one with sentinel nodes, and you'll see there's a difference. Yes, Noah?
So do the bottom, I guess, do they always point back to the parent?
Yes, so there's also not just the, so there's a parent link in each node, and they always point back. So here's pointing back, here's pointing back. So these are going to turn out to be helpful for doing certain operations as well. Okay.
I meant like they always point back to the very beginning.
The sentinel node?
Sentinel node.
So the leaf nodes always point back. Their children always point back to sentinel nodes.
Okay.
Leaf nodes do. Okay. Also, if something had, any time you don't have a child in either your left or your right subtree, that you point back to the sentinel node. And you all point to the same sentinel node. Other questions about that? Okay. So some fairly simple stuff is the constructor, the size, and the empty function. So size, you just return the size. Empty, you return true if the size is 0, false otherwise. To set up the tree, you need to create a new sentinel node, make its parent be null. Okay, the one case where you make the left equal null because it really should not point to anything, but right, you have it pointing back to the sentinel because initially it's an empty tree. Just like in a linked list, you had it pointing back to itself when it was empty. And then you set the size to be 0. Okay, so find, it could be implemented recursively, and I showed you that recursive implementation pseudocode for it the other day. But we want speed. Speed is important when we're doing searching, and it turns out that we don't have to do it with recursion. Okay? So here we're doing it without recursion. We start by going to the root. So string is the string we're trying to find, and we're going to be returning the value. So string is the key, we'll return its value. So we start by going to the root, then we enter an infinite loop, but we will have a way of getting out of that loop, infinite loop. So if the node is equal to the sentinel node, we return null to indicate that we failed to find the key in the tree. So null indicates that we failed. Okay? If the string is equal to the node's key, we return the node's value. If the string is less than the node's key, then we walk over to the left child, otherwise we walk to the right child. Okay, and you can see we actually do terminate this loop because eventually we're guaranteed to reach the sentinel node if the key is not in the tree. Now, Dr. Planck has a question. Is it okay for a value to be null? Could we have a value that is null? Answer is no. That would be a bad idea because null is the value we return to indicate that a key is not in the tree. So if we assign a key the null value and then we go looking for the key, we will think it's not in the tree. Okay? This is a similar problem to why we tell you not to use A to I. Okay, despite the fact, I know I'm doing a tangent, but despite the fact that we showed you how to convert integers to strings using string streams, some of you have been slipping into the bad habit of using A to I. A to I is considered to be a very dangerous function that you should not use. The reason is if the integer is 0, it is valid, and A to I will return 0, indicating it failed. Okay? So if you've been using A to I, please stop using it for the same reason you do not use null as a value in a tree. Okay? Because you can't determine in all cases whether the key is valid or not. Just like with A to I, you cannot determine in all situations whether the integer is valid or not. Okay. So, that was fine. If it was recursive, I could have written it recursively. So, it would have been more like I tried to do it recursively. This is always fun when you try to do it on the fly. First of all, I would have needed a recursive helper. Okay, so you can try to do it without one, but it's not going to go very well for you. The reason is to do the find operation, you really need to do I'll call it rfind for recursive find because I don't have a lot of space. I'm going to pass it the string s, and I'm going to pass it the sentinel right. So you can see the problem with trying to make find recursive is that actually I have to pass a second argument, which is the node I want to look at. And the user doesn't have access to the nodes in our tree. They're protected. So we want our API to only reflect the fact that they need to find a string. So the recursive version then, again, I'm going to write pseudocode, so I'm not going to write it perfectly here, would be recursive find, takes a string s and a node n, and we would say if n equals sentinel, return null. Else, if s was equal to n key, return n value. Else, if s less than n key, return recursive find on s and n left. Else, return recursive find on s and n right. So recursion and loops actually have a fairly close relationship, as you can see here. So the structure is very similar, except that rather than looping, we're returning the recursive call on either the left or the right tree. Now, making a recursive call or any kind of function call is expensive, which is why, if possible, we avoid function calls and instead use iteration. So questions about find. Okay, let's look at insert. So with insert, what we need to do is, let's say that we had Fred, Binky, and Luigi. Let's say we want to insert Smiley. We have to find the node that we're going to attach Smiley to, and that's going to be a node where Smiley would go. That location is currently empty. So you can see right now the right child of Luigi is where Smiley should go, and it's empty. So the first thing we want to do is we want to find the node where we're going to do the insertion. And it says this loop finds the parent. What it's doing is finding the parent of the node to be inserted. So it should really say this loop finds the parent of the node to be inserted. So in effect, our first thing to do is a find operation, or close to it. So that's what this code is doing, is we're first of all going to assume we don't allow duplicate keys. So if the key is already in the tree, we're going to return 0 to indicate that we failed. So this return value, int, indicates whether we succeeded or failed. So if the key is already in the tree, we return 0 to indicate failure. Okay, you'll see up here, we initially set the parent to be the sentinel and n to be the root. So initially n is equal to the root of the tree, and the sentinel is the parent. So what we're going to do, so we have the sentinel pointing here. We're basically going to be moving our way down the tree, okay, one at a time. So then we're looking at Smiley, and what we're going to do is we're going to move n so it points to Luigi, and the parent so it points to Fred. Then we're going to find that Smiley is greater than Luigi. So we're going to make n come down here, and what is n going to point to at this point? The sentinel. So n is actually going to point to the sentinel. and the parent is going to point to Luigi. So we know that we have found the place to insert Smiley when we reach the sentinel node. And at that point, we've kept a trailing pointer. So think of parent as a trailing pointer that's trailing in down the tree. And at that point, the parent pointer points to n's parent, which is where we're doing the insertion. So that's what we're doing here is while n is not equal to the sentinel, we set the parent to n. So we're moving the parent down to the current location, and now we're advancing n to go either left or right. Okay? So when we're done, our parent pointer is right here, and it points to the right location. So when we're done, now we're ready to insert. So we need to create a new node. So we'll create a new node for Smiley and make n point to it. Should be clear that we need to make the left and the right point to the sentinel node. We need to make Smiley's parent point to Luigi. And we need to make the parent node's right point to Smiley. So we need 4 operations. 1, 2 to set the left and right node, left children of Smiley to the sentinel. 1 to set Smiley's parent, and 1 to set the parent's left or right child to Smiley. So that's what we do here, now circled. We start by setting n to be a new node. We initialize the key in the value fields, make the parent point to the parent, make the left and the right point to the sentinel. Then, right here, there is one special case. If the parent is the sentinel, we need to make the sentinel's right be equal to n. So that's the case of the empty tree. We actually can't quite get rid of the fact that the sentinel node right here is the so-called, it's not part of the tree, and if the tree is empty, we have to do something special. Okay? Else, if s is less than the parent's key, we set parent's left to n because we know it must go into the left tree. Otherwise, we set the parent's right to n. So in this case, Smiley is greater than the parent's key, so we set the parent's right to be equal to n. Then we increment the size and return 1. Questions about that? Now, I want to show you something cool about sentinel nodes. Dr. Planck didn't do it. But I had this special case here, right? Okay, well, I don't care what the key value of the sentinel node is. It is not considered to be part of the tree. So what would have happened if I, at the very beginning of the insert, had set the sentinel's key to be equal to s? Okay? I don't really care about what the sentinel's key is. It's not technically considered to be part of the tree. But watch what that simple operation does at the bottom. At the bottom, I no longer would need the special case, this special case. Why? Because now, even if the tree is empty, okay, so we have a sentinel node as the parent, I've set the sentinel's key to be s. So when I do the comparison, is S less than parent's key? False. And I actually set parent's right equal to N. So in fact, most people who use sentinels use this trick. The fact that the sentinel not being part of the tree, I can put anything into that key field that I want. And thus I can get rid of that nasty little boundary case. That's one of the cool things about sentinels, is the ability to get rid of boundary cases. There's no harm done by doing that assignment at the beginning. The sentinel is not part of the tree. Okay, now let's just take a look at the book's version of insert. Okay, so they are using zeros as nulls. So when they do it, you'll notice they have a special case. If the tree root is null, they do a special thing for the tree right here. Otherwise, they default to the non-null case of the tree. Okay, and they also are always having to make a special check right there to make sure that the left or the right isn't zero. And the reason they have to do that is that they can't be going through a null node. If they do, they'll get an error. So without having the sentinel node, they're also having to do special checks to make sure that they're not advancing to a null node. But because we have a sentinel node, we don't have to worry about that. Okay, we always know that even if we've reached a leaf and we try to go beyond that leaf, we'll actually get a valid node. But the book is having to make some special checks to see if the left or the right is empty or not. Okay, something we don't have to do with sentinel nodes. Plus, with my little trick, I got rid of the special case of inserting into an empty tree. I took care of the boundary case. Okay, so the first two operations were easy, insert and find. The third operation, delete, is a little bit more complicated. Okay, so there's three cases, it turns out, for deleting a node. So with delete, there's three cases. Case one is the easiest. It's a leaf. If the node is a leaf, we simply delete it. There's no further thing. So if we delete Callista, there is no further consequences. So deleting a leaf is easy. Okay, case two, the node has one child. That's an easy case too. So let's say that instead of deleting Callista, we want to delete Daisy. What do we do if we delete Daisy? What do you think the easy thing to do is? That's right. So just promote the child to Callista's spot. So replace deleted node with its child. So it doesn't matter whether that child has itself, Alfred and Cindy, it doesn't matter whether it itself has children, because we know that it is also less than Daisy's parent, and therefore we have reestablished the binary search tree by simply promoting the child up there. All of the child's successors are still less than Fred, so everything is okay. So the hardest case is case 3, where the node has 2 children. Okay, so let's say we want to delete Fred. So there's no obvious thing to do for deleting Fred. So you might just say, well, let's promote Daisy, which works in this case, but let's say that we have Ellen. Okay? If we promote Daisy, there's no, what do we do with Ellen? Okay, there's no good thing. So it's not as easy as just saying, well, let's promote one of the 2 children. In fact, what we do is we find the the largest node in the right subtree. So delete the largest node in left subtree. Replace node with deleted node's contents. That's the solution to our dilemma. So for example, if Ellen, in this case where we're deleting Fred, the largest node in Fred's left subtree is Ellen. So we'll end up deleting Ellen and promoting Ellen up to Fred. Okay, so why does this work? Why can I be so confident that it works? Well, we're using the largest node in the left subtree. Okay, so we know that the largest node, so all keys in left subtree, must be less than the largest key in the left subtree, right? Other than the key being, other than that largest key. So all other keys in the left subtree are less than the largest key in the left subtree. So if we promote that node, we know that in the left subtree, we've maintained the binary search property. We also know that all keys in the right subtree are greater than the largest key in the left subtree. Why do we know that? How can we be so sure that all the keys in the right subtree are greater than the largest key in the left subtree? Yes?
They were greater than the original node that you're looking for.
That's right. They were greater. The reason is, so for any key R in the right subtree, it was greater than Fred, which is greater than any key in the left subtree. So any key that we choose from the left subtree is going to be less than Fred and therefore must be less than any key in the right subtree. So by promoting the largest key in the left subtree, we maintain the binary search tree property. Okay, so the second question you might ask is, how do I know that if I delete the largest node in the left subtree, that it will fall under one of the two easy cases. How can I know that if I delete the largest key in the left subtree that I won't have that nasty case 3 again? Yes.
If it's the largest in the left side, then it won't have a right.
Very good. If it's the largest key in the left subtree, it can't have a right child. Okay? Think about it. If Ellen has a right child, there's something greater than Ellen in the left subtree. So by definition, the largest node in the left subtree must have a null right child. So at worst, we're looking at case 2. We could be looking at case 1, which is what we actually have with Ellen. But at worst, we're looking at case 2. In fact, without Ellen in this tree, with just the original tree, it turns out that the largest child in the left subtree is Daisy. Okay? Daisy, in fact, has a left child, but not a right child. So if we deleted Fred, we in fact would promote Daisy. And Callisto would move up to there. Okay, as a here's a more complicated one with Fred. Now if we delete it, what are we deleting? Actually, take a moment. You all take a moment and figure out what you think this tree should look like. Feel free to talk about it with your neighbor, but what do you think this tree should look like after I delete Fred? Yes.
Fiona takes the place of Fred.
Very good.
Daisy has a right child, Ernie.
That's right. So Fiona is going to get deleted and replaces Fred. And because Fiona has a left child, Ernie replaces Fiona. So Daisy becomes the right child. I'm sorry, Ernie becomes the right child of Daisy. Okay? So any questions about this? Okay, so let's look at the deletion code. Actually, let's do one more example because it's actually seemingly easier but can be a little confusing. Suppose we want to delete, let's see. We want to delete, Luther. So if we delete Luther, then it's the biggest child in its left subtree is Luigi. So in fact, we delete Luther, replace it with Luigi, and it just looks like that when we're done. So there we go. Okay, so the code. Let's insert. Okay, so delete. First thing we have to do is find the, oh yes.
Is there any benefit to doing it the way that you showed us right there versus finding the smallest on the right side?
No. The question was, is there any benefit to doing it that way as opposed to finding the smallest node on the right side? The answer is it's 100% arbitrary. You just have to be consistent. You should either choose, actually, you probably could flip a coin and it might be more likely to stay balanced because if you have a lot of deletions and you're always taking it from the left subtree, it might have some balancing implications. But for simplicity and everything else, we just make an arbitrary decision to either always delete from the left subtree, but we could also have made the decision to always delete the smallest element from the right subtree. You just have to make an arbitrary decision. Just like with the Sentinel node, we arbitrarily made its right child be the root. It could have been the left child. We just have to make a decision. Other questions? Okay. So with delete, we first of all have to find the node to be deleted. Okay, so same thing we always do. While n is not equal to the sentinel and s is not equal to the key. And if n becomes equal to the sentinel, the key was not in the tree to begin with, so we return 0 to indicate the delete failed. So again, int indicates whether we actually were able to delete the key or not. If the key does not exist, then we return false. Okay, so once we have the node, we need to know what its parent is. Okay, because we're going to have to do some kind of relinking in many cases. At the very least, even if it's a leaf node, we're going to have to make that parent. So let's go back up for, well, actually, let's stay here. Even if it's something like, say, Fred, Binky, Luigi, and let's say I delete Binky, I still need to remap Fred's left child to be a pointer to the sentinel. So even in the case where the node we're deleting is a leaf, there's some linking that has to go on with its parent. So that's why we need to know the parent node. Okay, so we now check to see if there's 3 cases. They could be a leaf, could have 1 child, could have 2 children. So we start by asking, is n's left the sentinel? So if n's left is the sentinel, remember n points to the node to be deleted. So n points to node to be deleted. So we're saying if n's left child doesn't exist, so it points up to the sentinel, there are 2 cases. One is that its right child is also null and points to the sentinel, in which case n is a leaf, or it might actually point to a subtree. So there's 2 cases here. One is that this is case 1 where it's a leaf. This is case 2 where it has 1 child. Okay? So before we do that, we say if n is equal to the parent's left. So we know n points to the parent. So we have the parent. Okay, so there's 2 cases. The parent could n could be either the parent's left child or it could be the right child. In either case, we have to relink. Okay, so if n is the left child, we want the parent to point to n's right child. And if it's the right child, we still want the parent's right pointer to point to the right child. Basically, what we're saying is if, there we go, if the node n has no left child, then the parent should now point to its right child. And notice we don't care whether it's case 1 or case 2. In all cases, the parent should now point to the right child. If the right child is null, the right child points to the sentinel node. And if the right child points to a tree, fine. Now the parent points to that tree. So in either case, we have made the parent point to the right place. Okay, so this really picks up cases 1 and 2 simultaneously. Okay, now we have our test. If n's right is not equal to the sentinel, then we relink n's right's parent pointer. So basically what we're saying is if n had a right child, a real right child, its parent pointer used to point to n, we now need to make it point back to the parent. So that's the point of this particular piece of code. Rather nasty to read, but that's what it's doing. Okay? Now, it's not actually the end of the world if n's right was the sentinel, and we said that n right parent equals parent, it's not the end of the world if we set the sentinel's parent to be equal to the parent, because the sentinel's parent is irrelevant. Just like the sentinel's key is irrelevant and its value is irrelevant, its parent is actually irrelevant. The only thing we care about in the sentinel node is its right child. It's the only field that has any significance. So in fact, this test is not really necessary. And in Dr. Planck's original code, he didn't have it. However, one semester I had a student ask, well, what if it's the sentinel node? Isn't it kind of weird to make the sentinel node's parent point to something? I thought, well, to get rid of that question, I would just add this protecting if statement. Okay, and then when we're done, we delete n and decrement the size. Okay, so if n is not if n's left, so up here we said if n's left is equal to the sentinel. If it's not, then we have two possible cases. We could have case 2, which is that n has a left child but no right child, or we could have case 3, which is that n has both a left child and a right child. So we're now checking here, do we have case 2? If the right is a sentinel, we have case 2. Okay? So if it has no right child, we again replace the node with its left child. So again, we're just relinking the parents. We're finding out whether n was the left or right child. If it was the left child, we make the parent's left pointer point to the left subtree. And if n was the right child, we make the parent's right child be n's left subtree. So this is case 2 right here. This is the case where it just has a left child, and we need to make the parent point to that left child. Okay, same thing. Now there's no check because we know for a fact that n's left is not equal to the sentinel node. We would not be in this piece of code if n's left was equal to the sentinel node. So we know for a fact that n actually points to a left child, and therefore we can set that left child's parent to be equal to n's parent, delete n, and decrement the size. So we're finally left with case 3, which is we delete the smallest element in the left subtree, which means we have to find the smallest element in the left subtree, and that's how we do it. Starting at n's left, which we know can't be null because we had done the check to see if n's left was a sentinel node, and it's not. We now just chase down right pointers until there are no more right children to follow, because the right child is always the largest node. So we just chase our right pointers until we run out of right pointers to chase. And when we're done, MLC points to, when done, NLC points to minimum left child. That's what MLC stands for, minimum left child. Sorry, maximum left child. Now we save the key and the value of this child so that we can assign them to n, to replace n's contents with that. But before we do that, we recursively call delete on temp key. Okay, so you might wonder, why not just say, this looks so complicated, Brad. Why not just say delete temp key? Whoops. Why not just say delete MLC key and then say n key equals MLC key, n val equals MLC val. That would be so much cleaner. Why doesn't that work? Yes. Because MLC is no longer there. Delete blew it away. MLC is now a dangling pointer. Points to deallocated memory. There's no guarantee that MLC points to your deleted node. The memory allocator can do whatever it wants with the memory for MLC. It may have trashed it. So that's why we saved the values. Okay, so you may say, okay, that doesn't work. Very good. We'll just do this. Okay, because now it's clear that MLC still points to something, so we'll replace the contents of n, and now we'll delete MLC key. So why didn't I do it that way? That's also simpler.
Because then you have two elements.
Very good, because now I actually have two nodes in the tree that actually are MLC, and I'm going to delete the wrong one. I'm actually going to get, the problem is in this case, let's say I had Fred, and let's say it was Luigi. Let's say this was Linda, and this was Lori. Let's say, and this is Wayne. So let's say I want to delete Luigi. If I, before doing the deletion, I replace Luigi with Lori, well, the delete routine is going to try to redelete that one. Which means it will run down the tree to Linda, and it will find Lori. It'll say, oh, I'm going to delete Lori. I'll put Lori up here. What are we in? An infinite recursion. We, in fact, created something like an infinite loop. So that didn't work very well either. So that's why we had to save the values of MLC, then do the delete, then we assigned the contents of the deleted node to n. There's also something missing here. Notice The previous two things had delete n and size minus minus. We don't have that here. The reason is that this delete call will do the size minus minus and the delete for us. Therefore, it would be a mistake to delete n. We're not actually deleting n here. We're actually assigning it the contents of MLC. Delete took care of deleting MLC and decrementing the size by 1. Okay? We good with delete? I know that's a lot. You'll probably have to look at the code to see how to do it. But this is also an example of a recursion. Right here, delete actually recursively called itself in this case. So we actually use recursion with the delete. Now, the remaining operations all require tree traversals, which we will get to on Thursday, but I'm going to quickly give you a preview. So one of the deletes is to destroy the tree. Okay, so to destroy the tree, we have a tree. What we want to do is destroy its two subtrees first and then destroy the node. Okay, so the way we do it, first of all, we define a recursive helper that's going to call destroy on the sentinel right. Remember, the sentinel right is the root. So we must take care when we're doing our deletions to not delete the sentinel until the very, very end, because the sentinel tells us when we've reached the bottom of the tree. So in our recursive destroy, if we reach the sentinel, we return. We don't have any children. Otherwise, we first destroy our left tree, then we destroy our right tree, and then we delete ourselves. Okay, notice if we were a sentinel node, we didn't delete ourselves, we returned. So these three operations take care of delete left, delete the right subtree, and then delete the node. And then when I'm all done with that, I can delete the sentinel. Okay, that's the very last thing that I do. Notice that I don't delete any of the values. The reason I don't delete any of the values, even though they're also pointers, is because some other things might point to them. A general rule when you're destroying stuff in the destructor, only delete things you created, or objects. Only delete objects you created. So you didn't create the values, they were passed to you as pointers. The things you created were the nodes, and therefore that's all you need to delete. This type of traversal of the tree is called a post-order traversal, and we will talk about the three types of traversals at the beginning of class on Thursday. But a post-order traversal is one in which we do things to the children first, and then at the end we do something to the parent. Okay? So we'll get into traversals on Thursday. We'll also get into balanced AVL trees on Thursday and continue with those on Tuesday.